Welcome to this talk, and I'm so pleased to welcome back Dr. Clare Craig. Claire, thank you so much for coming back.
Thanks for having me, John.
Now, we're sharing some amazing animations today from I haven't actually learned to pronounce his name properly, I'm afraid, Erik Tangsoo in Estonia, filmmaker. And he's kindly given us permission to share some clips, which we're going to play now. But just before we do that, if you want to read the best book that's ever been written on the COVID pandemic as a summary, in my view, it's this one. It's still available, Claire. You can buy this on Amazon.
Absolutely, yeah.
Yeah. So do get that. We've done a couple of videos on this in the past and covered it in great detail. Anyway, without further ado, let's go on to the first clip. And this is really quite amazing. It teaches about science, pharmacology, cytology, and it just brings everything to life, basically. So let's give it a go. So we're looking at this first clip now from Erik. So we see a needle releasing lipid nanoparticles. And then we see all these lipid nanoparticles. So that's presumably sticking in your muscle somewhere and squirting in lots and lots of lipid nanoparticles. So just before we look at the circulation there, Claire, these lipid nanoparticles, I did a quick calculation once, and it seems that each vaccine dose contains thousands of billions of them, probably several trillion of these lipid nanoparticles. So they're absolutely tiny things.
They are, and I think that there isn't something we can compare them to particularly. It's a new technology, and the tininess of them it needs to be understood in terms of other things in the body, because you can't because they're much smaller than anything else that we have sort of dealt with in medicine. And so obviously that gives them different properties. And one thing I would say is what they do when they're making it is they put the mRNA into the solution, and because of it being charged, the mRNA gets sort of encapsulated by the differently charged lipids. So it sort of forms itself in the solution. But if you leave it over time, these tiny little lipid nanoparticles, they can coalesce with each other and become bigger. So over time you might get a whole variety of different sizes and therefore doses in any one lipid nanoparticle. But so this video is sort of the pharma story of what they ought to have looked like.
Yeah, these are the ideal lipid nanoparticles, and I've actually got a diagram I've just produced here. It's pretty basic, but it shows a red blood cell. So the big red circle is the red blood cell, and the small dots are the lipid nanoparticles. And the AI tells me that this line across the middle, that you can get 87 lipid nanoparticles will fit across one red blood cell. So we're assuming that the red blood cell is about 7 micrometers, that's 7/1000ths of a millimeter. And these lipid nanoparticles are probably around about 80, 90 nanometers. That's the next one down, Claire, isn't it?
Yeah, thousandths of a micrometer.
Yeah, thousandths of a micrometer, yeah. So do you know Erik, Claire?
Yes, I do know Erik. He is a very talented man who's worked incredibly hard. He's made several videos, like documentary videos about vaccine injury, and he's recently produced these graphics with a friend, as I understand it. But yeah, he's very motivated, and it's really interesting seeing how being motivated by truth can get these things out in a way that, he's not being paid to do this. No. He's really not got money as a motivation at all.
Yeah, it's proper intrinsic motivation, isn't it? He's done it because he believes it's the right thing to do, which is brilliant. And he's produced 2 films, actually. One's called Inside the mRNA Vaccines, and another one's called Inside the Vaccine Trials, both of which, of course, we'll link below in the description. And these graphics we're looking at today come from Inside the mRNA Vaccines, but this is just, generously has given us permission to share these just for general teaching purposes, which, of course, is remarkably generous. So this is the bit we've seen, Claire. So we've injected these lipid nanoparticles. Is there any physiological equivalence of sort of lipid nanoparticles in the body? I mean, when we were given these lipid nanoparticles, will the body sort of say, oh, these are lipid nanoparticles, I know what they are, or is it something new?
It's new, and I was just thinking through when you said that about what we don't know, because the problem is, we've got electron microscopy that can show things that are really very small, but I'm not sure it can really resolve down to a few nanometers like that. So I'm not sure we've ever been able to know what's there at that scale, actually.
Yeah.
It sort of becomes, you end up working on crystallography and things like that, which we know, which we have observed less with. And yeah, so of course, the thing is that the body is set up to deal with things that are foreign, and we have all of these things that have evolved to protect us. But they require the foreign thing to behave in a way that foreign things normally behave, right? So that they would come into the cell, by binding onto a receptor and hijacking the cell's equipment. And when they get into the cell, there would be sort of replication and double-stranded RNA and things that our cells can detect as viral invasion. Whereas the lipid nanoparticles just they get taken up in what's called endocytosis. So the membrane kind of takes a drink of the liquid that's around the cell and takes it into the cell. So it's an active process to bring it in. It's not just slipping in. But when it's in there, it's acting on the cell, and the cell doesn't necessarily have the mechanism to say, I'm being hijacked, and alert the immune system.
Right, I hadn't fully appreciated that, Claire. So I'd assumed that the two cell membranes kind of come together, and the lipid part of the lipid nanoparticle stayed outside, but the whole lipid nanoparticle goes into the cell. So you end up with this foreign lipid, as well as the mRNA, actually inside the cytosol of the cell.
That's right, and I'd also made that mistake. I'd also assumed it was just sort of membrane fusion that was happening at the cell surface, and it does happen like in the endosome once it's in. But I think it's quite an important distinction, because a lot of people have got worried about, cells that have had lipid nanoparticles in. If they're coming in just by sort of, passing through a membrane, they could just as easily come back out again. And so there was this kind of fear of what's going in the other direction. But I think because it's an active endocytosis that's bringing it in, it's mostly a one-way street.
So do we actually know what happens to this foreign lipid material once it's inside the cell?
Well, I mean, actually, I just realised I was saying all this and sounding very definite about it. Of course, all of this is sort of based on, it is based on some work. But it's. I think you always have to sort of cage it with uncertainty. We don't know everything, do we?
No. I mean, we do have this process called phagocytosis, so we know that this process occurs.
Yes.
The material is taken inside a cell, but that we normally associate that with neutrophils and macrophages and defense cells, don't we?
Yeah. So the phagocytosis is where you're gobbling up, material debris around the cell, and then using the inside of the cell to destroy it. So you're sort of mopping up dead things or mopping up things that shouldn't be there. Whereas this endocytosis, all the cells do it, and it's a way for them to kind of they pick up sort of what's going on in the environment around them. It allows them to uptake other things as well that they can use to sort of see what's going on.
But of course, the macrophages and the neutrophils, that they have the destructive digestive equipment in their cytoplasm, just ready to get rid of all this debris, just get ready to lyse these bacteria and viruses. But ordinary cells presumably don't have as much specialised digestive destructive equipment within them. So these lipid nanoparticles.
They do have some though. They do have some, but they don't. But then, I guess that takes us on to the next bit. Well, maybe we'll come to that when we're looking at the mRNA. But there's the question of, once you've got something foreign inside a cell, what's it going to do with it?
Absolutely, yeah. And the answer to a lot of these questions is I don't think we really fully understand that, do we? I certainly don't.
No.
Let's look at some more video. So we're at a stage now where we've injected probably between 3 to 6 trillion of these lipid nanoparticles, we believe. Although we're open to correction on that number, but it's one heck of a lot, that's for sure.
It is. When you sort of put that into context about how many cells there are in the body, you're in the same ballpark now.
Yeah, that's interesting. I think the last estimate I heard was probably about 70 trillion cells in the body.
Yeah. So you tenfold out, only 1 for every 10 cells. That's quite an astonishing number. Yeah.
So we've got potential here. Given that we've got systemic distribution of lipid nanoparticles, and that's no longer a debate, and we'll see that in a minute, for transfection in multiple cells.
Yeah, I mean, I think we have to be realistic about gradients and concentrations and stuff, and there are some cells that are going to get hit a lot harder than others, particularly the endothelial cells that line the blood vessels. They get exposed to a lot. As well as, obviously, the idea was it was going to go into the muscle in the arm, right? That was the idea. Those are the cells that were meant to be targeted, which is an odd thing in some ways if you just sort of take a step back and pretend that you knew nothing about, like, vaccine ideas. So why would you want to tell the body to attack muscle cells? Like, is there a respiratory epithelium you're meant to be trying to protect? Anyway, Moderna did a study, I think it was in 2023. They got funding to do a study to say they were going to look at what happened to the lipid nanoparticles that did not go into muscle cells. And in that publication, they stated that only 2% did.
Wow.
So they sort of were saying, it's very inefficient trying to get it into muscle cells, so we have to give you an awfully high dose. You're like, well, about the other 98%. So they say, well, we're going to find out what it does. You're like, really? In 2023?
Incredible. Let's look at some more video. Phenomenal graphics.
Yeah. I mean, this kind of graphic work takes a lot of effort.
Oh, heck yeah.
Yeah, they've done a beautiful job.
Yeah, and we see them circulating.
And you've got all those blood lining cells that are going to be exposed. And of course, the exposure is not going to be uniform even within a blood vessel, because if you get any kind of microclotting anywhere, or rather when you get into the very, very small vessels, everything's flowing much more slowly there. So that's much more of a chance for it to get to the edges of the flow of the blood and interact with the cell. And if you've got any microclotting, then you're going to get stagnation around that clot and more of an opportunity to enter a cell as well.
It didn't occur to me before that if you get like an aggregation of lipid nanoparticles, you're going to end up with a bit of a blob, and that in itself could be that could constitute a blockage in the small vessels, and that could potentially aggregate, presumably, clotting factors to it.
Yeah, so if they get really big, and they do get really, really big. So I don't know if you've seen the videos where people have taken mRNA vaccine liquid, put it onto a glass slide and looked at it under a microscope. And when you do that, you start to see coalescing to start with. Like, obviously, it's happening at a scale your eyes can't see, but it gets to a scale where it becomes microscopic and you can see it coalescing. And then they start to form rectangular crystals, which are cholesterol crystals, because most of the lipid in a lipid nanoparticle is cholesterol. And when cholesterol crystallizes, it looks really inorganic. You get right angles, perfect right angles, with the rectangle usually with the corner missing. Or you get, if you look at those in the other dimension, they look like needles because you're cutting them across the other way. So the point is that if you heat it on the light from a microscope for long enough, you start to see the whole thing coalesce into crystals, which are relatively enormous. And so it all depends, I guess, on how long they've been there, what temperature they've been at, as to how much coalescence has gone on. And if you get the big ones, then probably less likely to end up in a vessel unless it's injected directly into a vessel, which can happen. So Mark Girardi's done a lot of work on this. Do you know his bolus?
Mark Girardi, yes. I've talked to him several times. Yeah.
So the whole idea being that you've got that sort of when you inject into a muscle, you're putting in a liquid into a space where there wasn't a space. So you have a high pressure, like balloon of liquid, and when the needle goes in, you will break small vessels with the needle. So depending how near that needle is to the high pressure balloon of liquid, you're going to get a different dose entering the vessels, and it can be that the whole thing just gets squeezed right in, or it can be that it's diffused over a slower time. And I guess the size of the lipid nanoparticles might alter what gets into the vessel as well. I don't know what scale I'm on when I'm saying that. I might be wrong.
But people as well, many videos I've seen of people giving these injections, they seem to take a pride in how quickly they can do it and how painless it is. And of course, the more quickly you squirt it in, the higher the pressure is going to be and the more small blood vessels you're going to disrupt.
That's right. And I mean, it's the thing about Mark's work, really, the thing that sort of really hits home with me is when he's looking at studies from a long time ago, because this is something that's really, there was a huge amount of research on. And so that kind of idea around pulling back on the syringe before you plunge it all in, and whereabouts in the arm you should be aiming to increase the level of safety, was because they knew it was a problem for decades. In the 1950s, it was well established that 2% of people will have a deltoid injection hit a vessel with negative consequences. So, if you're going to accept 2% negative consequences, that you need to have a very, very large benefit to outweigh that risk.
Don't tell anyone this, Claire, but in 1975, my charge nurse told me how to find out the gluteus maximus, how to stick the needle in, and how to draw back. And this was ingrained into us like drill. Stick the needle in, stabilise it, draw back, and only then inject if you're not getting any blood. And yet, for some reason, these guidelines were changed. It's just inexplicable to me that all of the vaccine injections that are now being given are being given wrong because people aren't aspirating.
I mean, but realistically, the people who were injecting in those vaccine centres weren't they weren't qualified nurses.
Indeed.
They were volunteers.
But in the last few years, I've worked with qualified nurses who've told me that you don't need to aspirate when you're giving vaccines. I mean, I did, but the qualified staff are actually being taught the wrong thing by the national guidelines. It's rather bizarre.
Yeah, that is bizarre.
Yeah, it is. So basically what we're talking about so far, we haven't even started talking about the mRNA yet. All of these complications would occur purely because of giving these foreign lipid nanoparticles, even if they contained absolutely nothing inside them.
Well, that's right. And so lipid nanoparticles were worked up originally for gene therapy, right? So there's this idea that, if you've got a child usually, but, some of them are adults who've got a missing gene and they need that gene, and they need it in a lot of cells around the body. So they say, well, how can we get material to as many cells in the body as we can? And so that was the kind of impetus behind lipid nanoparticle technology. And when when BioNTech was sort of established, this was their realm, was, delivering genetic loads into cells. So they were looking at the lipid nanoparticle technology, and they were complaining about the toxicity of it because they knew you couldn't give repeated doses, because whenever they tried, there was too much toxicity associated with it. So they said, well, it's no good really for gene therapy because of the toxicity, but we could use it for vaccines because then you only need one dose. And of course, look at what's happened. People are 9, 10, I don't know what they're up to now, but they knew it was toxic.
Yep. Let's look at some more video. Yeah. Of course, the lipid nanoparticle, you see the lipid nanoparticle there, but of course we know the scale is tremendously smaller than the red blood cells we see in the background. I think this is just showing the idea that we've got systemic circulation of the lipid nanoparticles, Claire, with the blood.
Yeah, I quite like that as well for showing the flow.
Yeah.
That, if you've got a vessel that's got fast flow, then the chance of your lipid nanoparticle hitting the edge and interacting with the cell is lower. So, it's when you've got a stagnation somewhere or a smaller vessel that it's at most at risk.
And of course, in some capillaries, thinking particularly about the brain and the lungs, the capillaries are so small that the red cells have to squeeze down, don't they, to get through them?
Yeah, I've seen that under a microscope where they're all deformed and trying to get around the corners.
Yeah. Now, this next clip, Claire, I think we're showing this very process you've just educated me about, the endocytosis. Endo in cell, cytosis, cell going into the cell. So we see a whole lipid nanoparticle being subsumed into a living human cell, albeit in animation. So we've seen the lipid nanoparticle go in, and we've seen it deliver its payload of RNA.
Yeah, which is of course not where RNA should be in a cell. RNA in a cell should it's in the nucleus. It gets made in the nucleus, and it comes out into a part of the cell called the Golgi apparatus, where the proteins are made.
Yeah.
And so it's got a position to be in the cell, but this is coming in from the membrane and is sat in the cytoplasm.
Yeah, it'll go to the ribosomes, then onto the Golgi to be exported, won't it?
Yeah. And I don't know how much we know about what happens to random foreign mRNA. I mean, obviously we know it makes protein, so some of it's getting into that Golgi apparatus and is being used. But you think, well, how did it get there? Because the cell, it doesn't travel on its own. It's got to be moved. And so the cell has all this equipment that moves things around.
Yeah.
Something's moving it to there. And I don't know, some of it potentially is getting destroyed or it's getting spat out. But some of it does end up making protein.